All right, in this podcast, we're going to talk about the strength of polarity. So you figure out that something's polar, but how exactly strong is that dipole? All right, so just to recap, a dipole moment is basically the way to quantify the polarity of the molecule. It tells us how big of a difference there is between the partial positive and partial negative part of the molecule. We can find this value either indirectly through experiment or we can calculate it theoretically. And the dipole moment is measured in these things called debye. All right, so here you go. You see have three different molecules here, and you see that each of them has their own little dipole moment value. So the most polar one is going to be the one with the largest value, whereas the least polar one is going to be the one with the lowest value. All right, so it is customary to see, instead of partial positive or partial negative, a lot of times you'll see these dipole moment arrows. Basically what it does is it draws an arrow from the positive part of the molecule to the negative side of the molecule. So this little cross through the arrow, it's on the positive side. So that's kind of how I always remember it, is this is on the positive side and then it goes towards the negative side, which is the more electronegative element. All right, so going back to our examples a while ago, so we have these three molecules, and we know that this one is the most polar and this one is the least polar. And we're going to attempt to explain why this is the most polar and this one's the least polar. All right, so if you'll notice, down here we have a chart of electronegativity values. So you see that this first molecule, it has hydrogen in it, and it has nitrogen in it. Okay, so if we look at those values, we got a value of 2.1 over here and 3 over here. So the difference in the electronegativity in that molecule's atoms are 0.9. Now, for the NCl3 molecule, we've got a difference of nothing, right? So there's no difference between the electronegativity of N or of Cl. And then we look at fluorine and we have a difference of 1. Okay, so you're probably now a little confused as to why the differences in electronegativity values aren't really giving us the full story here, are they? Because this one has the biggest difference over here, and it's the least electronegative, but this one has the no difference between the two atoms, and it's got like medium polarity, right? And then this one's just slightly smaller difference than the least polar one. So this data is not giving us enough of the story, okay? The other thing that you need to take into consideration is these lone pairs, okay? So they all have lone pairs, right? All right, so this value is only telling us the pull in this bond right here. Okay, that's what this value is telling us. So it's telling us that there's a large difference between hydrogen and nitrogen's pull. So nitrogen is really pulling the electrons in the bond towards itself. Okay, so just the bonds itself are giving them there's some partial positive, partial negative. Then you've got this big lone pair on top, which is just really exacerbating that, okay? So you got a huge difference in partial positive and partial negative on this molecule. All right, now looking at this next one, we know that the difference between N and Cl is they're the same, right? So there is no difference. So this is not a polar bond. These are not polar bonds here. So what makes this whole entire molecule polar is that lone pair right there. So that lone pair gives a partial positive and partial negative to the molecule itself, okay? But it's not quite as big of a deal as there being polar bonds, like in this one over here, the NH3 molecule, that are pulling on So you have the nitrogen's pulling all these electrons this way and a lone pair, right? So you got all the electrons getting pulled this way and then the big lack of them here. Over here, you just got this lone pair that's overpowering the molecule and making it have a negative portion on this side and the positive portion on this side. So on this one, the polarity of the molecule is completely based on this lone pair. Over here, it's the lone pair plus the polarity of these bonds. All right, now over here, we have a difference in polarity of the bonds right here that is comparable to the difference between N and H. So this difference between these is about the same as the difference between the bonds in this first molecule, right? Except for you have a reverse thing going on here. So here the most electronegative element is here. So it's pulling the electrons in this bond between itself and nitrogen towards itself. So it's a different direction that the dipole is going. So if I were to draw the dipole arrows, it would be like this. Okay, so it's really pulling there we go, there's my arrow. So it's really pulling the electrons this way. So it's trying to make this partial negative down here by pulling all the electrons in that bond down. Also gives a partial negative charge to this molecule. So in essence, the pull of these polar bonds here between nitrogen and fluorine and then this lone pair, they essentially are canceling each other out, right? So that's why this one ends up being the lowest, because these polar bonds are counteracting that lone pair. All right, now here you see that you have the phosphorus trifluoride molecule and the nitrogen trifluoride molecule. And you see that they have a dipole moment of 0.23 and 1.6. So we want to try to figure out why, okay? So between nitrogen and fluorine, you see we have an electronegativity difference of 1.0. Okay, so nitrogen is less electronegative, so fluorine's going to pull it that way. Over here, between phosphorus and fluorine, you see that we have an electronegativity difference of 1.9. So again, phosphorus is less electronegative than fluorine, so it's going to be pulling towards the fluorine. So what ends up happening over here, why this one has such a large dipole moment, is because this electronegativity difference is so great that it basically pulls all the electrons away from phosphorus towards the fluorines, and basically it overwhelms that lone pair up there. So you end up with this basically a huge dipole going this way. Over here, your bonds are still polar, but they're less polar. So instead of overwhelming the lone pair, they just simply cancel it out, and you end up with a very, very small overall dipole. All right, looking here, we're going to rank the molecules in order of polarity. We want to go from the least polar to the most polar. All right, so if you're looking here, I'm just going to label all of our polar bonds. We know that CH bonds are considered nonpolar, but CCl bonds are considered polar. So we are going to draw some little arrows to indicate polarity, okay, for each of them. And then you see this one has none. So obviously this one right here is going to be your very least polar molecule. So this is the least polar because it doesn't have any polar bonds at all. All right, now this next molecule, if you'll notice the polarity, the polar bonds are kind of like opposite each other. So there's a little more symmetry here. So you're going to have more canceling out of these two bonds between themselves. So this would be the second least polar. All right, and then this next one, in general, you've got a dipole going this direction through the molecule as all of these are summed up. Again, these two are going to kind of cancel, and then this one right here is going to be the one that gives the overall polarity of that molecule. So this would be the third least polar. All right, and in this one, you see that the dipoles are going in the same direction. So basically, it's giving this whole molecule a pretty large dipole. So this would be the most polar one. All right. Next, we're looking at wanting to find the ones with the largest dipole moment in each pair. All right, so to be able to do this, you really got to have the structures. All right, there we go. That's better. So now you see that we have our molecules drawn out. All right, over here on the CS2 molecule, hopefully you notice that the geometry is completely linear. And when you have a linear geometry, automatically these dipoles between these polar bonds are going to cancel out. So the sulfur is a little bit more electronegative than the carbon, and so it's going to pull like this, and essentially these are going to cancel each other out, and there's going to be no dipole for that entire molecule. Okay, now this one over here, sulfur and oxygen. So if you know the placement of sulfur and oxygen on the periodic table, you would notice that oxygen is more electronegative than sulfur. So you're going to end up with this. Now, the thing that really kills this one is this lone pair. All right, so because of this lone pair, this actually is a trigonal shape. So it actually looks something like this in the real world. So because of that, you've got a electronegativity like this, and then this big lone pair is given a big overall dipole that's pulling the whole molecule like that, which means that this one definitely has the larger dipole of the two. So definitely this one on that pair. All right, now this next set that we're going to look at is H2O and OF2. So again, I need these structures. All right, there we go. Okay, so when you're looking at these, hopefully the first thing you notice is that we have the same geometry going on here. So these are both two lone pairs on the central. They're both tetrahedral bent geometries. So geometry is not going to come into play like it did in the last one. So we're going to have to rely completely on electronegativity here. All right, so when we get these dipoles in here, hopefully what you're seeing is that on this molecule, the dipoles are basically adding to the lone pair's negative charge up here. Over here, the dipoles are going against this over here. So that definitely means that this H2O molecule should have a larger overall dipole because the bonds are actually additive to the lone pairs, whereas over here there's some canceling out going on, so it's not going to be near as polar of a molecule. So definitely H2O wins in this case for having the largest dipole. All right, now looking at this last set of molecules, CF4 versus SF4, hopefully you see that there is a difference because CF4 has no lone pairs on the central, whereas this SF4 does have a lone pair on the central. So CF4 is going to be definitely a non-polar molecule because it's symmetrical. Everything's going to cancel out. All these CF polar bonds are going to symmetrically cancel each other out in a tetrahedral geometry. Now over here, we're definitely going to have some sort of dipole because we have this lone pair here that is not going to get completely canceled out. So in this case, the SF4 one.